Okay, so today I'm going to be talking about the data structure that is a skip list. So, to get started with a little bit of historical context, skip lists were first introduced by American computer scientist William Pugh. He first introduced these in a 1990 paper called Skip Lists, a probabilistic alternative to balanced trees. So, basically, before he wrote his paper, BSTs, so balanced binary search trees, were the main data structure used for efficient search, insert, and delete operations in O log n time. So when he was writing this, he wanted to find a good alternative that wasn't basically arrays and linked lists, but still had this like efficient time complexity. So let's see how he did that. So as you can see here, BSTs like AVL trees and red-black trees are efficient with their O log n time, but they can use strict balancing rules. They can be complex to implement because you have to worry about, for example, in red-black trees like red and black and keep track of a lot of different things. Rotations must be performed every time they are unbalanced, so global rebalancing. This means they're not the best for parallel processing because each rotation can change entire subtrees and many pointers can change across multiple levels. So it's not great when you're trying to do multiple different tasks at once if your tree is constantly changing so much. So we want something more localized. Is there a solution simpler than BSTs but with better time complexities than a simple linked list where you usually have to traverse the entire thing to do a lot of operations? Yes, the solution is skip lists. So, the way that a skip list is structured and organized is that they are organized in layers. A sorted linked list is the bottom layer, and each layer above it is the same elements as the bottom list, but with less elements at each level. These layers contain skipping links, allowing for shortcuts. So this is very efficient when you're looking for elements that may be far apart because we don't have to look at every single element when performing operations like with regular linked lists or arrays, and we can skip quite a few elements, hence the name. So overall, there's just fewer steps involved. Here's kind of a picture that compares a simple linked list to a skip list. The requirement is that level 0, so down here, this level, contains all of the elements in sorted order. So as you can see, this is an ascending order with numbers. The node pointers always point forward. There's no backwards pointers, like in a doubly linked list. And as you go up, the levels must become smaller. So as you can see, if we're like traversing here, on level 2, we get to skip 11 here and we go straight to 13, and it's basically just cascading up and down. These are kind of like the shortcuts, you can call them, these pointers. So let's look at how we insert into a skip list. Skip lists use probability and randomness for balancing, basically to decide like what nodes are going to make it to the upper levels. So the structure of each node contains a key, which is the actual data or value stored in the node. This data is used for ordering. So in the last example, that was the numbers. And then we have to store the forward pointers at each level. So for example, if we had an array called forward at index 0 for a given node A, it'll point to the next node, so what node A is pointing at level 0. And if node A still exists at the next level up, which would be level 1, forward at index 1 would point to the next node at that level. So if you can imagine here, 10's array at level 0 would point to 11, and then 10's array at level 1 would point to 13. And the way we decide if the node will make it to the next level is through the coin flip technique. So this determines how many layers a new node will be present in. So when inserting a new node, the first step is to call search, and this determines basically if the node already exists in the list, and if it doesn't, we will always insert in the bottom list because, again, every single node is present in the bottom list. And then to decide if we want to put it in the next level up, we flip a coin, quote unquote, and if it lands on heads, then we do add the node to the level above, and we update the pointers in the array. And if we got tails, then we just wouldn't do anything. We would stop at just the bottom list. But we basically keep flipping again and again and again until we get tails or we reach the max level possible in the skip list. So now let's look at how search works. This is really important because we also just used it in insertion before we actually place the node in the list. So what we do is that we start at the highest level, which is the top left node. This is going to be the level that has the least amount of nodes, so this is why we start there. And then we basically keep traversing that level to the right, so we keep going across the pointers to the right until either we find that node or we find a next node that is actually greater than the target. So this would be an overshoot. This means that we need to drop down a level because it might be in the next level. So we repeat this process until the target node is found or we reach level 0. And if it's not at level 0, then it's not in the list at all. So we would return the value if found or null if failed. Here's a note about how that actually works in code. So to drop down a level, we basically just subtract 1 from the array level. So if we are at level 5, but forward 5 surpasses our target, then we would just subtract 1 and check forward at 4. This may not make sense now, but let's see how it looks in an animation because it's easier to explain. So putting it together, I chose to show insert 19 because, of course, insert will call search first, so we can see how both of those work. Here we have a pretty basic skip list with just 4 elements. This is level 1 and this is level 2. Here's the sentinel. So we must search for 19 first. We're going to check if 19 is already in the skip list. It's not. And basically we record the last node before where 19 would be inserted at each level in an array. This array would probably be called something like update behind the scenes. We would use this when we want to insert later. So let's look at our top left node first, which is 8. So 19 is greater than 8. Should we move right? The answer is yes, because we're going to keep going as long as the current value is less than our target value. So let's check the right. But the right node is greater than our target of 19. So 19 is less than 30. Let's not keep going. We need to move down to check if it's in the bottom list. We go down and then we go to the right of 8, which is this node right here, which contains 10. 19 is greater than 10, so should we move right? The answer is yes. So we would check 30 again, and as in the last example, 19 is less than 30. We can't move right anymore, and we are already at level 0, so we cannot move down. And this means that 19 does not already exist in the list. For our purpose of inserting, this is a good thing because this means that we should go ahead and insert 19. So we want to insert 19 into the bottom list first. And again, we stored that the last node before its insertion would be 10 in the update array. So that's how we know where to put it in. So let's insert 19 in this spot right here. There we go. So we updated the pointers too. And now let's decide if we want to take 19 to the next level. So let's flip a coin. Usually in the implementation, the coin flip would be done with some sort of rand function. So let's flip it, 0.5 chance, we got heads. This means we do want to move up. So we stored in the array that we would want to insert it again right after 8. This is the last node before its predecessor, so let's update the pointers here. And keep in mind there are 2 pointer updates, so let's go ahead and see that. We want to insert on level 2. And here we updated 8's forward pointer to the new node, which is 19, and we updated 19's forward pointer at level 2 to point to 30 right here. So now let's flip a coin again to see if we want to move on to the next level. Keep in mind we're going to keep flipping until we either hit tails or we surpass the max level. So the max level is predetermined and could be anything. It could be like 5, it could be 10. So here, if we haven't reached the max level, which would be level 2, we can keep going. So let's flip a coin. Let's see what we get. We got tails. So we do nothing. The insert was successful, and here is our updated skip list with 19. So now let's analyze the time complexity of these operations. The search is going to be O log n, and the reason for this is because if you think about it, the number of nodes halves at each level based on probability. Again, this is amortized, so this is like on average. The coin flip is going to make it so that at level 0 we have all of them, and then at level 1 we have half of those nodes, and then at level 2 we have a fourth of those nodes, and it keeps going. The next would be 1/8. So yeah, in each search, we will likely not have to explore each of the levels. The average cost is roughly log n then, because you're basically having the amount of nodes that we have to look for using shortcuts over a sequence of searches. Again, this is not guaranteed because it all depends on probability. So the worst case is ON. This is very unlikely, again, because of the coin flip system, but if we have a very heavily skewed tree, it might degenerate into a linked list. Imagine basically we just flip tails over and over and over again, so the nodes never move on to the next level, and we just have one long bottom list. That basically would be a linked list, hence why we would get ON, because we have to traverse everything. So then, insert, the time complexity is very similar because each insert contains a search, which we just covered up here, and then a series of coin flips, and then the updating of pointers when we're inserting at each level. So each coin flip has a constant time complexity, and each updating of pointers, only 2 pointers are updated per level, which is also a constant. So what ends up happening is we have the time complexity of search, which would be either O log n or ON, plus constant time plus constant time. And as you know, we would basically ignore these and we would just get O log n or ON. And here's the comparison table, your skip list, and then linked list and array and binary search tree. As you can see, this is with average time complexity, not worst case, because we're basically mostly looking at the average case here. It's very similar to the binary search tree, which was Pugh's intention when he was writing that essay. So what are the pros and cons and trade-offs of using this data structure? The pros is that it's very reliable, it has quick insertion and search, and it has a pretty easy implementation and understanding compared to BSTs and hash tables. We don't have to rotate anything, and we don't have to constantly rebalance the entire tree, because remember how in BSTs, a lot of times you have to move the head pointer and do like left-right rotations and stuff like that. The cons are that this requires more memory than a BST because each node can have more than 2 pointers, and then one node can exist on multiple levels, unlike a tree. So this is a lot more memory. Reverse search is not allowed, we can't go backwards, and it's not cache friendly because the items aren't stored contiguously like in an array, they're more scattered throughout memory. So we would not want to use this when we have limited memory because of all the pointer overhead, or we have small data sets because the time complexity of this data structure is going to increase with like the more levels we have, or when we need a strict performance guarantee, because again, we can't guarantee that we're always going to get the average performance. But we would want to use this when we have problems with parallel processing or a lot of concurrency when we're doing a lot of tasks at the same time, because we don't have to rebalance the whole tree. We want a simpler implementation than BSTs, or we have sorted lists. Remember, that's one of the requirements with frequent operations like search, insert, and delete, because those are quite fast. So this would make sense in an implementation like Discord tracking what members are online at one moment. This is actually one of the real world uses of a skip list, because users are constantly entering and leaving chats. So we need to do operations on that list of users quite often. And then here are my references. Thank you so much for listening. That was all for my presentation.